Hello? Okay, now you can hear me. Yes, so thank you very much for coming to my talk, and thank you to the organizers for inviting me. And as Tachapul said, I will speak about dynamic string algorithms. So unlike pretty much all talks in this workshop, this won't be about graphs, but about strings. So let me start by saying what a string is. So a string is a very simple object. It's just a finite sequence of characters from a given set, which we call alphabets. And in string algorithm, we are studying various problems about strings. And those which you might have heard of include pattern matching or lossless compression algorithms, compressing, decompressing, and so on. Or some other wide family of problems is that of computing string similarity measures such as edge distance or the longest common subsequence. And today I will share some of the results about dynamic versions of these fundamental problems. So after this very brief introduction to string algorithms, I will move on to how dynamic strings are modeled. So what kind of operations on dynamic strings can we support and how the strings are maintained. Then I will survey some of the recent results in dynamic string algorithms. And then in the second part of the talk, in the second main part, I will share some technical details behind the main technique, which is combined with some problem-specific techniques used pretty much in all of the problems surveyed in the first part. And then I will share some open problems and final remarks about this research direction. So let me move on to the setting. And the basic setting is that, well, we maintain a string, and this string undergoes some changes. And various algorithms support various levels of those changes, various types of operations. Perhaps the most basic one is a substitution. So in a substitution, we are maintaining a string, and then an update asks to change a character at a given position to some other character. And here you can see an example where the fifth last character is changed from B to an A. In particular, for a substitution, you cannot really change the length of the string, and you just change individual characters. So that's some algorithms are restricted just to this operation, but more often than not, we are interested in something more powerful. And the next step would be to support also insertions and deletions. So now, again, we can modify any individual position, but now we can modify it by inserting some new character, like this red A in the third string is inserted in the middle of the previous string. And the converse operation would be to delete this character. And now you can start from an empty string in particular, and you can build any string using a sequence of insertions. A slightly more advanced operation, which is supported by many algorithms, is what I will call cut-paste, which you are probably familiar with from your favorite text editors. And this is no longer a local operation. In some sense, it's more global because you can select a fragment of the text, and it can be an arbitrarily large fragment. Here I've selected these 4 characters. And you can take this fragment, cut it, and paste it somewhere else within the text. And yet another operation, which is fairly similar to cut-paste, is that of copy-paste, also familiar from text editors, where we select, again, arbitrarily long fragment, this time the green one, and now we keep the original copy, but we also paste a copy somewhere else. And if you want to undo this operation, this is sometimes called uncopy, where we have 2 copies of the same fragment, and we can delete one of them so that we can go back, we can undo the operation. So that's the basic model, and most of the algorithms I will discuss support some prefix of this operation. So either just substitutions or all the edits, meaning indels and substitutions, and some of them also support more advanced operations like cut-paste or copy-paste even. So this is one model for individual strings, but often we also want to maintain some collections of dynamic strings. And historically, this is also a model that has been fairly well studied in the dynamic strings algorithms. And now, the basic operations are splits when you take one of the strings specified by the user and split it into some prefix and complementary suffix. In this case, the second string is split into the prefix of length 3 and a suffix of length 1. And the user also specifies where to split this string. And then the converse operation is that of concatenation, when you are taking 2 strings from the collection in an ordered pair, and we concatenate one string after the other. Here we are appending the first string after the second one, and we get this string of length 7, AB, AAB, ABBA. These 2 operations just like substitutions earlier cannot change the total length of the string in the collection. So you can complement this setting, for example, by adding 2 new updates, namely insertions of single-length strings to the collection and deletions of single-length strings in the collections. And now this model is becoming pretty powerful. In particular, it can simulate many of the operations from the previous model of maintaining an individual dynamic string. For example, if you want to implement a single deletion of a character, what you can do is you can split out this character by 2 split operations, one immediately before this character here, and then immediately after the character. And then you simply delete the length 1 string and concatenate the remaining 2 pieces to form the original string with just the character removed. And technically, this is often much easier to implement splits and concatenates than deal with all kinds of edits where some character is changed, substituted, inserted, or deleted. So these are 2 models we will be studying, we will be looking at in this talk. And let me now move on to the main part of the presentation, which is some survey of state-of-the-art results for dynamic string algorithms. So the most basic problem, which is actually trivial in this offline setting, is just testing equality between strings. This problem has reached quite a long history, over almost 30 years now, and historically it's been studied in this dynamic string collection model. So here we maintain this dynamic collection, and apart from supporting updates, we have queries, and these queries simply take 2 strings in the collection and ask whether these 2 strings are equal or not. So the collection can be a multiset. And here are the state-of-the-art results for this problem. Namely, there is a very simple Folklore algorithm, which I will actually discuss in the second part of the talk as a kind of warm-up, which achieves logarithmic update time. Here, n is the total length of the string in the collection, and the query time for equality queries is constant. And while this algorithm is randomized, here you can notice that the output of the queries is uniquely determined. So that's just a yes/no query. So we don't have the problem of leaking random choices made internally within the algorithm. So typically in these kinds of problems, we fortunately don't need to distinguish between oblivious and adaptive adversaries, like we have seen that's a major issue for approximation algorithms in the dynamic setting. So this is the Monte Carlo algorithm, which is very easy, and I will show it later. But the logarithmic running time has also been achieved using a weaker model of Las Vegas randomization a couple of years ago. And if you look at some of the earlier paper from SODA 2000, we can see that also that deterministically we just need to pay some poly log n term to the update time. So the original algorithm from this SODA paper by Alster, Brodal, and Rauer works in log n log star n, but it's actually randomized. So in order to randomize it, we need to use deterministic dynamic dictionaries, and thus we pay this extra poly log factor, which I'm here hiding under this little o of 1 in the exponent of the update time. Nevertheless, the query time is still constant. This is the fundamental problem, and we want to have it quite well understood. So the natural question is, what about this log n? Is it necessary? And it turns out that yes. You have an unconditional lower bound, so a self-slope lower bound using prefix sum problem. And this lower bound says that even if you allow Monte Carlo randomization and even if you allow amortized running times, all those previously mentioned ones are worst case, we cannot support both updates and queries in sublogarithmic time. Nevertheless, this is only for this dynamic string collection model. And in particular, I think that it's a nice open question whether you can lift this lower bound to the setting where we just maintain a couple of strings. So we maintain just 2 strings. And say subject to character edits, so insertions and substitutions, and we want to answer after each update whether the 2 strings are equal or not. So hypothetically, this could have some faster solution, but so far we don't know anything faster, and even we don't know anything simpler than just using the techniques behind the 2 algorithms working for the more general setting of dynamic string collections. And a fairly useful generalization of equality queries are queries asking to compute the longest common prefix of two strings and also to determine which strings is lexicographically smaller than the other. And here you can see a pair of strings. The green prefixes are the same, so the first 9 characters are the same in those strings, and you have a mismatch at the 10th position, which is indicated by these red characters. And here you can see that thus the longest common prefix length is 9, so the answer to the LCP query is 9, and that x is smaller than y, because the 10th character in x, a, is smaller than the 10th character in y, which is ab. And now, the very same data structures from the previous slide can also be also naturally work in for this more general setting. However, for the simple Monte Carlo algorithm, the query time degrades to log squared n. And thus, we are actually more primarily interested in the other two solutions, which use the locally consistent parsing technique that I will cover in the second part of the talk. And this is actually historically one of the first applications of this powerful technique. And here I must mention that these LCP queries are perhaps the most useful black box tool that's used in pretty much all dynamic string algorithms, and even sometimes outside this world. For example, one of the algorithms for a subset sum for a modular subset sum problem is based on these LCP queries in dynamic strings. But another generalization of equality queries is pattern matching queries. So this is one of the many ways to port the classic pattern matching problem into the dynamic setting. And now, instead of just asking whether one string in the collection, which I'll denote p, is equal to the other string, which I'll now denote t, we are asking to compute all the occurrences of the pattern p within the text t. And in this example, the occurrences are underlined in green, so these are the fragments exactly matching the pattern. And here again, the two more advanced solutions from the previous two slides can be used to answer the pattern matching queries. Here I am not including this Monte Carlo solution because its running time is very bad for the pattern matching queries, so it's no longer a question of polylog overhead. But for pattern matching queries, the latter two solutions based on locally consistent parsing can still be adapted. And here the running time the query time depends on two quantities. The first one is the ratio between the length of the text and the pattern. And this is fairly necessary. That's because that's how much information we can get from the set of starting positions of the occurrences. So even to achieve this query time, we need to encode those occurrences quite efficiently in terms of some arithmetic progressions. And then there is some overhead on top of that, and this overhead is currently log squared n for the randomized solution and slightly over logarithmic for the deterministic solution. And here you can see that the situation is quite different from what it used to be for LCP queries in particular, and that's because, quite surprisingly, the deterministic solution turned out to be more efficient than the randomized one in terms of the query time. So at some point we believed that the Las Vegas randomized solution is like this technique, which I'll show later, is like the best one you can hope for, but now with this result, we need to come back to the older deterministic implementation of locally consistent parsing, and we can see that sometimes it has significant advantages, and it can reduce the query time for this problem. So now this naturally gives rise to some open questions, like can you do some trade-off between the two solutions? Can you get the best of the two worlds in particular? And also here we have this T over P term, and while it's necessary for reporting all the occurrences, we can hope to reduce it for the decision version of the problem when we just ask whether P has at least one occurrence in the text. And so these are the three kind of black box problems which are used as subroutines for more advanced queries. So let me now move on to more global to queries working in this first model of maintaining one or two dynamic strings. And the first of these two problems, perhaps the most natural one, is another variation on the pattern matching problem. This is called text indexing. And now we maintain a long dynamic text or dynamic string t, and you ask for pattern matching queries, but this time the query string, the pattern, is given by the user at query time. And again, the same data structures with some adaptations, which in particular degrade the update time, because on top of the locally connected parsing, now we need to store some more advanced data structures. But still, the same techniques can achieve log squared and updates, and queries which have a linear dependency on the pattern, which is kind of necessary, some dependency on the number of occurrences, which is logarithmic overhead, provided that we do need to report the occurrences. For the decision version, this plus OCC log n term it vanishes, and then there is some extra additive term, which, for example, can be removed if you do not want to support the copy-paste operation, just character edits and cut-pastes. So this is, as far as the Las Vegas algorithm is concerned, a deterministic version in the most recent implementations has some extra overheads of log to 1 plus little of 1. And these overheads actually are quite annoying, meaning that given that in the previous slide we have seen that the deterministic solution for pattern matching is slightly faster than the randomized one, it's probably we should work a little bit harder for this text indexing problem as well and try to reduce the overheads in this solution. Another generalization of text indexing is the problem of maintaining a dynamic suffix array. This is actually what I will speak about later today at a STOC session. But just very briefly, this suffix array is just a way to encode lexicographic order between the strings, between the suffixes of your string, and here underneath the starting position of each suffix, I have marked the lexicographic rank of this suffix. So in particular, the entire string is a suffix of rank 6. So if you ask for the rank of this entire string, you should report 6. And the inverse query of asking the 6 smallest suffix should return a suffix of full length, which is 24, starting at position 1. And here, we managed to achieve polylogarithmic update and query time using, again, the locally consistent parsing. And this works up to copy-pastes, but for copy-pastes, we have some non-trivial lower bounds, namely the orthogonal multi-vector conjecture, which you have seen on the during Omri stock. It shows that if you want to update, in particular in polylogarithmic time, then you cannot hope for a query better than nearly linear. Another important family of queries is that of compression. So as you have seen, compression, as I have mentioned in the first slide, compression is one of the fundamental problems in string algorithms, and thus it has been studied very recently in dynamic strings as well. And here, what we can use is you can use the text indexes from the 2 slides ago, and this text index can be extended to report the compressed representation of the text. And here, this works both for Lempel-Ziff-like compression, which is in particular used in gzip, for example, and what's called run length encoded BWT, which is the core of bzip2, for example. However, here we just want to compute the compressed representation, so it's not surprising that we need to spend time at least proportional to the length of this representation with some polylogarithmic overhead. But interesting questions are whether you can just compute the size of the compressed representation more efficiently. So this might be a little bit difficult, but for LZ77 and for LLBT, because they are very volatile measures, in particular they can change quite a lot by a single edit, but there are some more well-behaved compressibility measures like substring complexity, and for which this is one of the problems that I think should be studied in near future in the dynamic setting. And then the list of problems goes on and on, like longest common factor problem. You find the longest substring which is common to the 2 strings. We have a polylogarithmic time solution very recently, but this one supports only substitutions. There is some unconditional lower bound. And here we again have natural problems. Why just substitutions? Well, hopefully you can also support edits, or the log to the 8n time also doesn't look to be optimal. Another of these problems include maintaining something called repetitive fragments. So here you can see this B is repeated quite a lot of times. Here also this substring is repeated 2 times and a little bit. And here the interesting phenomenon is this one of the problems where we hope to get a polylog update, but are not there yet. So the current state of the art is n to the little of 1. but I believe that polylog should be possible. And also, this solution, as is written down in the original paper, is just for substitutions, and I don't see any significant challenges why it shouldn't be ported to to stronger set of operations. So far, all the problems I have discussed admit linear time solutions in the static setting, and that's one of the reasons why we were hoping for very efficient dynamic algorithms lacking polylog and time. And the two final problems I will discuss are also quite challenging in the static setting. And this includes the famous problem of computing the edit distance and the length of the longest common subsequence. So in the dynamic setting, the fairly natural interpretation of this problem is just to maintain two strings, and after each update, you want to report the edit distance or the length of the LCS. And this admits nearly linear dynamic solution with nearly linear update time. It supports edits of characters, and you can easily see that this solution is fairly optimal. So we know that conditioned on the orthogonal vectors conjecture or the set hypothesis, we cannot have truly subquadratic time algorithm to compute the edit distance in the static case, and thus in the dynamic version, we also cannot hope for anything truly sublinear. However, the edit distance problem has been studied quite a while, including many papers on top conferences from various perspectives, including in particular approximation algorithms. And that's one of the white spots in the dynamic string algorithms, I would say. So currently there are no papers about approximating edit distance in the dynamic setting. Also, we don't know much what happens if the edit distance or the LCS are small. And in these cases, there are subquadratic time static algorithms. And a simpler version of LCS is that of longest increasing subsequence, which is quite interesting. It turned out quite interesting in the dynamic setting. In this problem, you are just maintaining a sequence, traditionally a sequence of numbers, and the goal is to maintain the length of the longest increasing subsequence. That is the one which I denoted in red. And here, the state of the art has been is from STOC last year. Namely, in two papers, there was first of all the first truly sublinear time dynamic algorithm, and the achieved update time is roughly n to the 2/3. And also, there is a PTAS in polylogarithmic update time and polynomial dependency on epsilon. However, for this problem, we don't even have any reasonable lower bounds for the exact scenario. So hypothetically, it's possible that there is a polylogarithmic time exact solution, and we just don't know it yet. Also, the sublinear time exact solution is Monte Carlo randomized, and it's not clear how to achieve anything sublinear in using deterministic or even Las Vegas randomized algorithms. All right, so after this pretty long survey, let me move on to some introduction into the main technique behind pretty much all the algorithms I have discussed so far, and this is locally connected parsing. And as I have promised, first I will give as a warm-up the main technique behind this Folklore solution for maintaining equality in dynamic string collections. And the main tool in this algorithm is what's called Karp-Rabin fingerprints or polynomial hashes. And this is a way to assign an integer to a string, interpreting the characters of the string as coefficients of some polynomial in a finite field. And the two properties of this function are that when you have two distinct strings, then with high probability the fingerprints will be also distinct. So the collision probability is n over p, and if you set p pretty high, that's inverse polynomial. And also, you can compute the fingerprint of the concatenation very efficiently from the fingerprints of the two individual strings. And using these two properties, we can easily implement equality by maintaining a balanced binary tree on top of each string in the collection W. And here, this is a regular binary search tree, and the only property of it we are using is that each node maintains the fingerprint of the string composed by the characters represented in this tree. So here, leaves correspond to individual characters, and for each node, we store the fingerprint of the string when you read out the leaves in the subtree from left to right. And now splits and joins of strings can be interpreted as splits and concatenations can be interpreted as splits and joins of the binary search trees, and these operations have been pretty well studied in the data structure community. In particular, there are some BST implementations which supports splits and joins in logarithmic time. For example, AVL trees satisfy this condition, and that's why we can implement concatenations and splits in logarithmic time using this method. And checking equality reduces just to finding whether the fingerprints stored at the roots of the two trees are the same or not. If they are the same, then with good probability, we can tell that the two strings are actually equal. So this works pretty well for equality, but already for computing the longest common prefix, we see some problems. So here you have two strings with fairly long common prefix of length 6, but the trees on top of these strings do not share much in common. In particular, we do not have any common prefix of these trees. And that's why the best we can do with this method is just, yes, and the main reason why this is the case is because the shapes of these trees is pretty arbitrary. So even if the strings were equal, the shape of the trees on top of them do not depend on the content of the strings, but actually how they have been created using these splits and concatenations. And that's why the best we can do for LCP queries is to do binary search and use splitting to check whether the prefix of a given leg is common to both strings, and that's why this algorithm has this degraded log squared n query time for computing LCP. So the technique which is used to handle, to overcome this difficulty is an actually pretty old one, almost 30 years now. And it dates back to two papers from 1994, one by Melchor, Sundar, and Urik, which is the first paper to study equality in dynamic strings. And also it appeared in a paper in the distributed suffix tree construction by Sachinalp and Vishkin. And here the idea is still to maintain a tree on top of the string, but now the tree should be constructed in a consistent way, meaning that the shape of this tree should be determined by the contents of the string, unlike in the previous solution where it was primarily dependent on the history of how the string has been created. And we want to have this property not only globally for the entire strings, but also locally. So whenever a string has two equal fragments, what's on top of them in the parse tree should also be very similar. So why is it useful? So for example, if you want to compute this longest common prefix, when we are guaranteed that what's on top of the longest common prefix is pretty much the same, we can quickly skip this common part and descend from the root immediately using some pretty short path to the position of the first mismatch between the two strings. So that's very useful for LCP, for comparisons, in which case it gives some polylogarithmic time speedups. But it's even more crucial for the more advanced operations like pattern matching. So in pattern matching, we are in particular heavily using the fact that for each occurrence of the pattern, what's on top of these occurrences is pretty much the same. And thus, instead of looking all the way to in the leaves when the pattern is quite long, we can take a look somewhere higher here when the pattern can be encoded in just a few consecutive symbols in the parse tree. So for pattern matching, this locally consistent parsing is no longer giving polylogarithmic speedups, but polynomial factor speedups. And also locally consistent parsing, local consistency of the parsing is necessary to maintain global consistency, and that's because you can imagine that when you have such two fragments, the user will come and ask to split out the two fragments using 4 split operations, and since split should be implemented pretty efficiently and in the worst case time, we do not have much resources to change the shape of the path tree on top of these fragments. So this is the main idea behind these techniques, and there are quite a lot of technical challenges to implement it well. So first of all, there is an issue with repetitive fragments. So in particular, here you have a very simple example of repetitive fragment. So it's a string consisting of all A's. And what we postulate that for each, say, length 4 fragment, the tree the part of the tree on top of it, it should be the same, or pretty much the same. So for these two, it is actually the same. But now here it's very different, meaning that here, for example, the first and the second character share the same parent, but here it's the second and the third one. And in general, it breaks the consistency property we've been postulating. And this is why, yes, and this should be true for all those fragments. And this is why, for highly repetitive strings, we need to resort to using run length encoding, which in this parsing setting simply means that we build a high degree node in the parse tree. And these high degree nodes leads to some technical complications in the algorithms, but these high degree nodes will have isomorphic subtrees. So we will have high degree nodes with isomorphic subtrees beneath them, and they will be composed of copies of the same character, or as we go up in the parse tree, of the same substring. So all the locally consistent parsing schemes are constructed in a bottom-up fashion. So we start with the string, and then we parse it, alternating between this run length encoding, which simply gathers matching adjacent characters, like these two A's are gathered in a single symbol, and I labeled this symbol by a C. And then we have some parsing step, which distinguishes between various flavors of locally consistent parsing, which tries to assign parents to some of the children. So some of the nodes, like this BA, is grouped into F. And the consistency pretty much means that the second occurrence of BA is also grouped into the same F. And this way we proceed bottom up until we have a single character, and that's how the whole parse tree is constructed. And let me now discuss a little bit more what kind of parsing mechanism can be used to implement this main parsing step of the dynamic of locally consistent parsing. So here the decision we need to make, as you can see on the previous slide, is whom to merge, whom to assign under the same parent. And this equivalently, this can be interpreted as where to put a boundary between children of one node and children of the next node in the next level of the parse tree. So whenever we scan the text, we need to make a decision. In particular here, we need to decide whether B and C should have the same parent or not, whether we need to phrase what's called a block boundary between these two symbols or not. And the consistency condition postulates that this decision should be made based on just the local context of this region of the text. So in particular, in this example, the decision should be made only on the characters within the rectangle consisting of 4 characters, 2 characters before the place where we are deciding about, and 2 characters after this location. So let's say that here we decide to put a block boundary. So in particular, this AB will have a different parent than the C following them. And then we proceed to the next position, and also we need to make such a decision. And let's say here we don't put a block boundary, and here we don't put it again. And here we arrive again at the context we have seen previously. So ABCA is a context we have seen earlier, and that's why we are bound to the decision made earlier. So in this case, we must put a block boundary, otherwise our mechanism wouldn't satisfy the consistency property. So this context size is one of the parameters characterizing various parsing mechanisms. And there is also another one, which is block size, which will roughly correspond to the possible degree of nodes created using this parsing step. So for run length encoding, the degree is unbounded, but in this case, we can control it. And there are the 2 families of solutions we have seen throughout all the previous slides, namely the Las Vegas randomized one and deterministic solutions, originate from the two different parsing mechanisms at this step of implementation of locally consistent parsing. The first one, which originates from works of Jesch, is what leads to the randomized solutions. And here, the main ninth property of this mechanisms is that the context is of constant size, actually of size 2. But on the other hand, the block sizes are sometimes 1 and sometimes 2. And this 1 is slightly annoying. And because if you keep producing blocks of size 1, you don't progress building the parse tree. But we are guaranteed that on average, the block size is at least 1.5, and thus we can still guarantee that the height of the parse tree is logarithmic with high probability. Another mechanism which originates from some techniques in the distributed algorithms, namely in, for example, finding an independent set in a list, is that of deterministic coin tossing. And here the context size is log star n, and this log star n needs to be paid in some polynomial exponents, or sometimes once, sometimes multiple times in the running times of dynamic algorithms. But the main advantage is that not only is the structure deterministic, but also the block sizes are between 2 and 3. And thus we have what's called local compression, that we don't have any regions lagging behind just because they are keep forming blocks of size 1. So these are the two techniques. At some point we are hoping that the compression will be always faster, but it's not the case. And more recently, it turned out that for some applications, these techniques needs to be tweaked a little bit. Namely, when we are looking at the context sizes, sometimes these context sizes cannot be just measured in terms of the length of symbols in this string, but also we need to look into how these symbols expand, because these symbols are like at higher level of the parse tree, these symbols represent some longer substrings, and in this restricted version, we need to make sure that no region compresses too fast, and thus we need to somehow pause processing for symbols which grow too fast. And in some applications, like in the pattern matching queries, this allowed some polylogarithmic speedups, but for example, in dynamic suffix array, this was one of the crucial steps to achieve a polynomial speedup, so to achieve polylog rather than a polynomial update time for the data structure. So this is the main technique, and actually this technique is used in all the algorithms I have discussed previously, with just 3 exceptions: array distance, LCS, and LIS. All the others use this locally connected parsing as one of the key components, and this is of course combined with problem-specific tools, which have typically been known from some other variants of the same problems in some other models, like space-efficient implementations or simple offline algorithms. And this locally connected parsing is not only used in dynamic algorithms, it's actually been designed also for parallel string algorithms, and it's still useful there. It's also useful for processing compressed strings. So when you want to do something on compressed strings without decompressing them, then also locally connected parsing is one of the main tools. But as I said, it comes in several variants, and we don't have very good understanding why it is the case. So it would be nice to have one unified variant that we could always use, but so far this is not the case, and the differences are not just log factors, as some of the more advanced problems witness. Also, this technique is pretty heavy technically, so that's why I couldn't go into much detail during this talk. And that's actually the reason why, even though the technique is pretty old, we haven't seen much progress in between, let's say, 2000 and 2010. So only recently, the community started to kind of rediscover this old technique and observe that with some tweaks, this locally connected parsing can be used to solve a wide variety of problems. But this is like a main challenge, I think, slowing down the progress in the dynamic string algorithms. There have been some attempts to counter this issue, like to hide all the technicalities in some black box. To some extent, it's been successful, but for very isolated problems like approximate pattern matching, where we have postulated some interface, and this interface hides all the technicalities of locally connected parsing, yet still is rich enough to support some approximate pattern matching problems. Okay, so this has been the main technique, and let me just conclude with some open questions and some other final remarks. So as you have seen in the last few years, pretty much all fundamental problem classes have witnessed some progress in dynamic setting. But I believe that this is still that the picture is not particularly complete yet. In particular, while preparing this talk, I have managed to identify some problems which could be interesting in the dynamic setting, but so far hasn't been studied at all. For example, Hamming distance in the dynamic setting. So Hamming distance is easy to maintain if you just support substitutions, but when anything more needs to be supported, we don't know pretty much anything. And why it might be interesting is that it actually has some non-trivial complexity in the compressed regime. Also, as I have said earlier, this substring complexity, maintaining substring complexity or some well-behaved substring complexity measure other than substring complexity is something that probably should be studied in the dynamic setting. And also, approximate edit distance is well studied statically, but so far nothing is known in the dynamic scenario. If you ask for concrete open problems, perhaps the most exciting ones are those when we have some polynomial gaps stemming from existing work. And this includes computing edit distance bounded by some threshold. So far, we have just this algorithm which works in nearly linear update time for the unbounded setting. But if k is slightly smaller than n, or significantly smaller than n, we don't know anything significantly better, unless k is really very small. Then for this LIS, we have a large gap. We have n to the 2/3 update time, and hypothetically, this could be polylogarithmic. And for example, for this exact pattern matching in dynamic collections, we had this factor t over p, and for the decision version of the problem, it's not clear why it should be there. Then a few of those very fundamental problems have been studied actually also up to log factors. In most other works, log factors are not optimized, but in the fundamental ones, like equality or pattern matching, they have been optimized. Yet still we have some gaps. So as I have mentioned at the beginning, this lower bound log n for maintaining equality probably might be liftable to the setting of equality of two dynamic strings. For pattern matching, we have this surprising result that the deterministic version of the locally connected parsing, the one based on deterministic coin tossing, is actually faster, and we don't know if this can be achieved without this log star n comprising, which stems from this larger context size. So this is another interesting question. And finally, there are little smaller improvements possible throughout most of the problems. In particular, the log factors haven't been optimized too much. The richness of the updates supported haven't been optimized so much. The deterministic versus randomized questions, and so on. So this is, I think, what could be studied next. And this is also the end of my presentation. Thank you very much for listening, and I'll be happy to answer some questions.
Any question for Thomas? So actually, is there like some lectures or like a survey on this locally consistent parsing?
Not really, unfortunately. So there are a couple of papers, but these papers are like typically at least 30 pages long on just this locally connected parsing. So I guess like that's kind of that's one of the missing things in the community, I would say.
All right, then. Thank you, Thomas.
Thank you. Thank you.
Okay, so basically this is it was the last talk, and so that's the end of the workshop, and I hope that you get some overview of dynamic algorithms, and so yeah, I think even if you don't care much about dynamic algorithm, I really hope that this workshop at least convey the fact that we have developed some general techniques, some algorithmic techniques that actually is kind of general enough and might work across the model, and that might be what we want as an algorithmic designer at the end of the day. And so basically, first I want to thank all the speakers and my co-organizer, Sayan, which is not, he has to leave already, and thank you all for participating. And so there will be some junior-senior meeting. So you can just like try to meet with each other. And okay, after this. And so that's it. Thank you very much. Yeah.